Alright, so now we're on OEH 5723, homework set 2, problem J. And in this case, we are wanting to create a standard atmosphere of xylenes. And so it says xylenes with an S because there's ortho, meta, and para xylene. And unless they really go through a lot of distillation process, xylenes tend to be mixed. So we're wanting to check the calibration of a direct reading device, maybe something like a PID. This is the sort of thing that I do all the time, but I do it with toluene. So we're told that we have a chamber with a volume of 1.13 cubic meters and that it is static. How many milligrams of xylene must you evaporate in the chamber to create 100 ppm concentration at 25 C in 1 atmosphere? So, first off, let's start with xylene. So xylenes, their molecular structure is a benzene ring with a methyl, and then if it's orthoxylene, you'd have another methyl there. If it's metaxylene, you'd have a methyl group there. And if it's paraxylene, it'd be opposite. So this is ortho, meta, and para positions. So 1 away, 2 away, 3 away. So it really doesn't matter which one it is. It has the same molecular weight in any case. And the molecular weight is 106.2. I looked this up on NIOSH Pocket Guide. So 106.2 grams per mole. Knocked over one of my journal articles. So 106.2 grams per mole, and we are trying to create a 100 ppm atmosphere in some sort of exposure chamber or some sort of chamber that we have. So in this chamber, this is where we want the 100 ppm to be. And we're told that it's 1.13 cubic meters. Alright, so what we need to do first is realize that we're trying to get milligrams. So this is really quite simple. We just convert our 100 ppms into milligrams per cubic meter and then multiply by our volume. And that will tell us milligrams per cubic meter. So 100 ppm multiplied by something with mass, in this case the molecular weight, so 106.2 grams per mole, divide by something with volume. In this case it's going to be the molar volume, which is 24.45 at 25 C in 1 atmosphere, and that's liters per mole. Our moles cancel, and again we're left in grams per liters. This is going to be a factor of a million off, which offsets our ppm, the million of ppm. So this gives us a direct output of milligrams per cubic meter. Here's my calculator. So 100 ppm times 106.2 grams per mole divided by molecular volume, by molar volume. So this should be 434 milligrams per cubic meter. Now I can also look online, and you'll notice that the PEL, the permissible exposure limit for xylenes, is 100 ppm. And NIOSH Pocket Guide also gives that to us in milligrams per cubic meter, and they say it's 435 milligrams per cubic meter. And so we've got 434. So there's just some sort of rounding error between them and us. It's nothing to worry about. So this is what I calculated. This is what I'm going with. So now that I've got this concentration, I've got a volume, and that if I multiply by a volume, then that gives me mass, right? So I'll be left with milligrams. So 434 times sorry, 1.13. Type the wrong number. So basically 490 milligrams. So that's good to know, but toluene xylene is a liquid. So the next step that you might be asked on the test would be something like, how many microliters of this, or what volume would you need to inject into this chamber? So you'd have to do all of this, and then you would just take it one step further and find the density of, or the specific gravity, the density of this solvent, and change this mass unit into volume units. So the density, just for your own edification, you can stop viewing now if you're only wanting the answer. We would have the density is 0.86 grams per mil. And so if we have 490 milligrams, a gram per mil is also equal to a milligram per microliter, because this is 1,000 times smaller and this is 1,000 times smaller. So this grams per mil can also be milligrams per microliter. So we have 0.86 milligrams per microliter multiplied by 490 milligrams. And that doesn't do us right. We've got to divide by our density. Divided by 0.86 milligrams per microliter. So it gives us microliters effectively in the numerator. And so how many microliters would that be? That'd be divided by 0.86. So 570. So what that means is you would have to inject roughly half of a mil to achieve this concentration. So if you're selecting a syringe, you would have to go find a syringe that's bigger than a half mil. So probably a 1 mil syringe would be your choice, because they come in 500 microliter and 1,000 microliter increments. So you'd inject 570, and you would make your standard atmosphere so that you could verify that that direct reading device, like that PID.